On behalf of our team, we thank you for the opportunity to present our climate health and environmental epidemiology research. And unfortunately, Mackenzie's unexpectedly not able to join us today. So I will try to carry the torch for us all. And thanks to the wonderful speakers, Drs. Harper and Houston, who already detailed the importance of climate change and health. And so we're going to jump right into it. We outline our talk as follows. So first, we're going to identify climate change vulnerability framework and the subpopulations who experience higher vulnerability. Then we explore associations with the environment to help select indicators. And finally, how we incorporated those indicators to map a vulnerability index for climate change health impacts. Our city level study is marked by the red patch in the province of Alberta. Amiskwaciwâskahikan, also known as the city of Edmonton, is divided into 1,196 census dissemination areas. And it's the unit of our analysis and mapping for climate change vulnerability. Vulnerability is the predisposition to adverse effects. And in our changing climate, older adults and immigrant communities, among others, may face greater vulnerability. And our main goal was to build a vulnerability index based on the city's IPCC accepted dimensions for these communities in Edmonton. And the 3 dimensions of this framework include exposure, contact with a hazardous substance through air, water, skin, or ingestion that can affect populations, sensitivity, characteristics that can increase risk of experiencing the exposure-related adverse outcome, and adaptive capacity, ability to adjust to potential damage, to take advantage of opportunities, or to respond to consequences. And each of these dimensions consist of multiple environmental indicators. And we examined hundreds of potential indicators for each dimension based on built social and natural environments from publicly available data sources. And we selected the final indicators for the index based on expert opinion, so known relationships found in the scientific literature, and regression models, so in biostatistical and spatial temporal analyses, where indicators were explored as predictor variables for health outcomes that are susceptible to climate-related events and air pollution. And we focused on cardiovascular, injury, mental, and respiratory health outcomes for analyses, guided by our results from a scoping review. Our health data came from the Discharge Abstract Database and the National Ambulatory Care Reporting System, and we assigned the unique records with valid postal codes in the city of Edmonton to the dissemination areas for our analysis. And we conducted an ecological correlation study using data aggregated at the dissemination area level to explore how exposure to climate and air pollution related hazards impact health, and how different community level covariates affected this relationship. And we modeled relationships using negative binomial regressions, and associations were measured as prevalence rate ratios. And this work is based on Mckenzie's master's thesis, which he successfully defended last month. We produced a lot of results in this exploratory analysis, and this table summarizes the trends we observed. Briefly, whether increased exposure to a climate or air pollution related hazard influenced community health depended on the health outcome. But generally, increasing temperatures and air pollution were risk factors. Low socioeconomic status and social isolation were strong risk factors, while access to green space and a favorable active living environment tended to play a protective role. Higher proportions of older adults and refugees in the dissemination area were associated with increased risk, while higher proportions of economic immigrants was protective. And the other regression analysis involved spatial data science, where we used space-time pattern mining to identify hotspots of each health grouping. So we input the 2-dimensional locations of the dissemination areas using 1-month time intervals for the 3rd dimension to calculate a space-time cube of monthly proportions for each of the health groupings. And the 3-dimensional cube was analyzed to identify emerging hotspots, which were ultimately represented as 2-dimensional areas that have more or less occurrences of the proportions of health events over space and time. And the resulting maps were reclassified as hot, shown as red, or not hot, shown as white. And so clockwise from top left, we see hotspot patterns for cardiovascular, injury, respiratory, and mental health. And the hot and not hot locations were then used in logistic regression to identify associations with each of the environmental indicators. And the size and direction of the coefficients indicated that higher air pollution and greater diurnal temperature were strongly associated with cardiovascular and mental health. And people who live in areas with more industrial pollution and less greenness tend to have more physical injuries. And there were not enough respiratory hotspots to calculate statistical associations. However, the traditional modeling did find relationships. So putting this all together, after compiling all the indicator selection methods, remember we had 3 different ones. We had expert, the biostatistical, and the spatial. This first table lists the 15 indicators for the sensitivity dimension. And we use the inverse of some of the variables to reflect the appropriate directionality. And note that the population-related variables were adjusted or geographically weighted by dividing the counts by the population per square kilometer of each dissemination area. And this next table lists the 12 indicators for the exposure dimension. And this table lists the 7 indicators for the adaptive capacity dimension. And the next steps involved combining each set of indicators into their complete dimensions. And we applied principal components analysis, or PCA, to the indicators. This map shows the results of the sensitivity dimension, specifically for older adults and immigrants in Edmonton. And the darker colors indicate higher principal component values, and the lighter colors indicate lower values. White indicates where some of the indicators had missing data. And this map shows the exposure dimension. Again, darker colors indicate higher principal component values, and lighter indicates lower values. And this map shows the adaptive capacity dimension. So we integrated those 3 dimensions using an unsupervised machine learning technique known as multivariate clustering. This gave us 3 vulnerability clusters as combinations of the dimensions, illustrated by the standardized box plots here and shown in this map. Yellow areas have high sensitivity, high exposure, and low adaptive capacity, and the brown areas have medium sensitivity, low exposure, and medium adaptive capacity. The green areas have low sensitivity, medium exposure, and high adaptive capacity. And so knowing this, each area will benefit from a corresponding reduction or increase in the relevant indicators that contribute to the dimension of interest. So understanding climate change vulnerability is an important aspect of adapting to and mitigating risks among older adults and immigrants. So therefore, we have shared the results in a community-focused interactive web mapping platform to inform planners and policymakers on which extreme weather and air pollution events threaten the health and well-being of older adults and immigrants, and identify areas where the impact may be higher and where action may be required. So I realize this is a rapid fire talk, but if you want more details, you can go to our website with links to a technical report, user manual, and an interactive story map, and I'll copy that link into the chat so you can explore that later. So on behalf of our team, we wish to thank our funders for their support and you for your attention. We're so grateful for this opportunity to share our local solution to addressing global health.